Here, I will briefly explain about some of the basic terms. Variance is considered as the measure of the spread of the data with respect to the mean in one dimension. Covariance is considered as the measure of the difference between each pair of the features, so it is used to compare features together. If the covariance is positive, it shows that both of the features increase together. If it is negative, one increases while the other one decreases. If it is zero, then two features are independent. The covariance matrix has variances on the diagonal, covariances off diagonal, and it is a symmetric matrix. So let's see what principal component analysis is. PCA is a statistical approach that converts a set of possibly correlated features into a set of linearly uncorrelated features using orthogonal transformation. In other words, we would like to find the most important features using PCA. The parameters that we would like to keep in a high-dimensional dataset are the ones that are uncorrelated, which means that they show low covariance, and the ones that change a lot in magnitude, which show that they have high variance. Since they have big magnitude, they are the opposite of the noise. In PCA, we need to change the bases and the representation of the data in order to find which features are dependent on the others and can be omitted. In this change of the bases, we will be able to find the principal components and project the data on them. So the main goal of PCA is to find a representation that eliminates redundancy and noise. The elimination of redundancy is equivalent to decreasing the off-diagonal values of the covariance matrix. Eliminating the noise is equivalent to increasing the on-diagonal values of the covariance matrix. So let's put it this way. In PCA, we need to find some orthonormal matrix P where y is equal to px, such that the covariance matrix of y called S of y is diagonalized. When S of y is diagonalized, it means that the off-diagonal values, which shows the covariance between pairs in lower dimensions, are close to zero, and the on-diagonal values are high, which shows that we are ignoring the noise in the data. In this case, the rows of the matrix P are the principal component or the new basis for representing X. According to the following relations and formulas that you can see here in this slide, if we choose P as the eigenvector matrix A, which is equal to X times transpose of X, then we can easily diagonalize the covariance matrix S sub Y. It must be noted that in this case, rows of X represent the features, while the columns show the samples. Thus, the covariance matrix would have the dimensions equal to K times K in the case that K shows the number of the features. So the algorithm of PCA includes the following steps. First of all, we need to subtract the mean of each feature from the actual values of the data. This step is called the data normalization and can be done using z-score method, which will be explained more in the next video. Then, we must calculate the covariance matrix of X times X transpose. At the third step, we need to compute the eigenvectors and eigenvalues of the covariance matrix. These are the principal components of X. Then we must choose the most important components as the principal components. They must have the greatest eigenvalues compared to the others. So at first, we should sort the eigenvalues and choose the eigenvectors with big eigenvalues as the principal component. It depends on the problem that how many of these features must be kept and what percentage of data we need to preserve. The new representation of data with fewer features is found by y equal to px, in which p shows the principal components of X.